Efficient random generator for very large range in Python. I am trying to create a generator that returns numbers in a given range that pass a particular test given by a function foo. However, I would like the numbers to be tested in a random order. The following code will achieve this. The problem with this solution is that sometimes the range will be quite large. Number might be of the order 10 *** 8 and upwards. This function can become slow, having such a large list in memory. I have tried to avoid this problem with the following code. This works well most of the time, since in most cases number will be quite large. Foo will pass a reasonable number of numbers, and the total number of times the __next___ method will be called will be relatively small. Say, a maximum of 200, often much smaller. Therefore, it's reasonable likely we stumble upon a value that passes the foo test and the size of tried never gets large. Even if it only passes 10% of the time, we wouldn't expect tried to get larger than about 2,000 roughly. However, when number is small, close to the number of times that the __next___ method is called, or foo fails most of the time, the above solution becomes very inefficient, randomly guessing numbers until it guesses one that isn't in tried. My attempted solution. I was hoping to use some kind of function that maps the numbers 0, 1, 2, n onto themselves in a roughly random way. This isn't being used for any security purposes, and so doesn't matter if it isn't the most random function in the world. The function here, create a random bijective function which has same domain and range, maps signed 32-bit integers onto themselves, but I am not sure how to adapt the mapping to a smaller range. Given number, I don't even need a bijection on 0, 1. Number just a value of n larger than and close to number, using whatever definition of close you see fit. Then I can do the following. So long as the bijection isn't on a set of numbers massively larger than number, the number of times index is lower than or equal to number isn't true will be small. My question. Can you think of one of the following? A potential solution for mix_function_factory, or even a few other potential functions for mix_function that I could attempt to generalize for different values of number. A better way of solving the original problem. Many thanks in advance.
That may be a case where the best algorithm depends on the value of number, so why not using two selectable algorithms, wrapped in one generator? You could mix your shuffle and set solutions with a threshold on the value of number that's basically assembling your two first solutions in one generator. The random solution, for big values of number, works well because there aren't so many repeats in the random generator.
The problem is basically generating a random permutation of the integers in the range 0, and 1. Luckily for us, these numbers have a very useful property. They all have a distinct value modulo n. If we can apply some mathematical operations to these numbers while taking care to keep each number distinct modulo n, it's easy to generate a permutation that appears random. And the best part is that we don't need any memory to keep track of numbers we've already generated, because each number is calculated with a simple formula. Examples of operations we can perform on every number x in the range include addition. We can add any integer c to x. Multiplication. We can multiply x with any number m that shares no prime factors with n. Applying just these two operations on the range 0, and 1 already gives quite satisfactory results. Looks random, doesn't it? If we generate c and m from a random number, it'll actually be random, too. But keep in mind that there is no guarantee that this algorithm will generate all possible permutations, or that each permutation has the same probability of being generated. Implementation. The difficult part about the implementation is really just generating a suitable random m. I used the prime factorization code from this answer to do so. Now that we can generate suitable values for C and M, creating the permutation is trivial. And your generator function can be implemented as
Getting the best performance in Python is much trickier than in lower-level languages. For example, in C, you can often save a little bit in hot inner loops by replacing a multiplication by a shift. The overhead of Python bytecode orientation erases this. Of course, this changes again when you consider which variant of Python you're targeting. PyPy? NumberPy? Cython? You really have to write your code based on which one you're using. But even more important is arranging operations to avoid serialized dependencies, since all CPUs are superscalar these days. Of course, real compilers know about this, but it still matters when choosing an algorithm. One of the easiest ways to gain a little bit over existing answers would be by generating numbers in chunks using numberpy.arrange and applying the x plus c *m% to the numberpy array directly. Every Python level loop that can be avoided helps. If the function can be applied directly to numberpy arrays, that might even better. Of course, a sufficiently small function in Python will be dominated by function call overhead anyway. The best fast random number generator today is PCG. I wrote a pure Python port here, but concentrated on flexibility and ease of understanding rather than speed. Zorashiro 128 Plus is second best quality and faster, but less informative to study. Python's, and many others, default choice of Mersenne Twister is among the worst. There's also something called SplitMix 64, which I don't know enough about to place. Some people say it's better than Zorashiro 128 Plus, but it has a period problem. Of course, you might want that here. Both default PCG and Zorashiro 128 Plus use a 2 n-bit state to generate n-bit numbers. This is generally desirable, but means numbers will be repeated. PCG has alternate modes that avoid this, however. Of course, much of this depends on whether number is close to a power of 2. In theory, PCG variants can be created for any bit width, but currently only various word sizes are implemented since you'd need explicit masking. I'm not sure exactly how to generate the parameters for new bit sizes, perhaps it's in the paper, but they can be tested simply by doing a *2 jump and verifying that the value is different. Of course, if you're only making 200 calls to the RNG, you probably don't actually need to avoid duplicates on the math side. Alternatively, you could use an LFSR, which does exist for every bit size, though note that it never generates the all zeros value, or equivalently, the all ones value. Edit. I figured out that this is untrue. Simply represent the advanced step as a matrix, and exponentiate it to jump. Note that LFSRs do have the same obvious biases as simply generating numbers in sequential order based on a random start point. For example, if RNG_outputs A, B, all fail your foo function, then RNG_outputs B will be much more likely as a first output regardless of starting point. PCG's stream parameter avoids this by not generating numbers in the same order. Edit 2. I have completed what I thought was a brief project implementing LFSRs in Python, including jumping, fully tested.